Hello, welcome to Richardson RFPD's Tech Chat. I'm Kirk Barton, Field Application Engineer for Richardson RFPD, and I'm here today talking with Eric Benedict, Senior Application Engineer for ADI, and we will be discussing Common Mode Transient Immunity. Eric, can you explain Common Mode Transient Immunity as it relates to gate drivers?
Sure, Kirk. So common mode transient immunity basically is the ability for the isolated gate drive to reject the disturbances that happen when the power converter is doing normal switching action. So basically, when the converter switching turns on a high side or low side switch, moving the switch node between the bus and the minimum voltage, either 0 or negative. And as this node moves up and down, it's going to charge capacitive in the capacitance of the isolation barrier. And so you have some current flowing through that capacitor, and that can cause disturbances to the gate drive's operation. It can be anywhere from just a small minor jitter, can cause in timing, or it can be, large where you get incorrect behavior, or even, in some cases, potentially damaging the isolator.
Okay. So you see a wide range of CMTI specs from 30 kV per microsecond up to hundreds of kV per microsecond. Are all CMTI specs measured in the same way?
Well, they can be, but if I take a step back and talk about the range for the specs that they have, you need to have different levels of performance depending on the switch that you're working with. So some older devices will have, like IGBTs, they switch slower, and they can use a isolated gate driver that has a lower CMTI rating because the switch doesn't switch as fast. If you're looking at using a newer switch device like a Silicon Carbide, those can switch easily, over 50 kilovolts per microsecond. So if you have a gate driver that was developed for IGBTs or slower switching devices, they can have problems when you have the fast switching edges of the modern devices. And then, of course, as every engineer knows, you want some margin. So just because it doesn't cause it under normal operations, you may want to have even more room for immunity for your CMTI, because if you have fault conditions or other things where the circuit impedances change because of, say, the fault, you can get even larger common mode transients that are happening, and you want your gate drive to still behave properly even under those conditions. So, would recommend with new devices, you really want, 150 kilovolts per microsecond to make sure that the gate drive does what you want when you want it to.
Okay. And are there different levels of common mode transient immunity that kind of dictate kind of controls or I should say, like, important levels to be aware of and how it impacts the switching signals?
Yeah. Well, you can look at how that common mode transient, impacts the performance. One metric that we like to use is looking at the impact that it has in the timing waveform. So for example, here, this is one of our parts, the ADUM 4120, and you basically have an input signal that's happening here, and then there's an output signal that's coming out of our test fixture. And this scope captures an infinite persistence plot, so we've done multiple traces all on top of each other, and then we're sweeping in the top trace a common mode transient that is applied before anything's happening, during the signal transition, and afterwards.
Okay.
And this is the level of performance you want to see in a gate driver, that the timing performance of the gate drive doesn't have any impact with the common mode transients that are applied. If you start to have impact on the gate driver timing, here, this is a different part, a slightly different disturbance level, but here you can see that the jitter, normally, this is what it should be doing, but with the disturbances, you can make the timing get a little bit faster or a little bit slower. So you get this jitter. Now this is still it's still an acceptable part, because if you look at the specifications, this is the maximum datasheet propagation delay. So you're getting some jitter. It's not as repeatable, but it's still within spec. So this would be considered, still operational. Here, the time scale is a little bit zoomed out because you're trying to show this, but basically here we're having a disturbance that occasionally causes the gate driver to misperform, and now the propagation delay, when you hit it at the right time, causes it to fall outside the timing performance of the specifications.
Right.
So these are kind of a progression that you're having, and then if you really hit the part hard and it can't take it, you can induce, what's called a static error. So here we have a transient, but there's no switching that's supposed to be happening. But even though, but we have this transient, and that causes the part to still change state. So you absolutely don't want this. This is causing an error.
Right.
Okay.
So is there like a minimum perhaps that you should look for as far as CMTI when it comes to fast switching GaN and silicon carbide?
For silicon carbide and GaN, you're going to really want something at least 50 or 100 to 200 kilovolts per microsecond, because you want something that's going to be immune to transients that are higher than what you're going to see in your application circuit. So we recommend at least 100 kilovolts per microsecond, if not more. And here you can see we've got a transient, again, our 4120, no jitter or minimal jitter here, very little error, and a similar competitor's part, and it's having some problems there. So
Okay. Yeah, that's a nice summary of common mode transient immunity. Can you go through some of those points as far as how that actually translates into the performance of the switching device itself?
Yep. Well, the big thing that you want to be able to have is, a short dead time, so that you're able to control the switch and get the switch back on, as quickly as you can to minimize your losses. And having, defined good repeatable timing, that's going to let you switch that faster, so you'll get higher performance in your converter.
Okay. All right. Very good. Nice summary. Is there anything else you'd like to add, Eric?
No, I think we've talked about it. Just,
okay.
Remember that, CMTI is an important thing, and, make sure you pick a part with sufficiently high CMTI.
Great. Thank you, Eric. We appreciate your time today, and thank you all for watching our Tech Chat video. You can learn more about this and other topics on the Richardson RFPD GaN and SiC Tech Hub. Follow our Ask an Expert link to submit questions relative to design challenges you may have.